To start out by looking at the traffic jam thing that we were working on last class. So we just go back a page or two. We had this table, right? Number of pairs, right? A pair is 2, so the number of sets of 2 people. And then the next column is the total number of people, right? So when you have 4 people, that's 2 pairs. All right, so we said it was 3 moves, and then what'd you guys get when you had 4 people or 2 pairs of people? 8 moves. What about when you increased to 6 people? 15. 24.
35.
Hold on. Did anybody actually use 10 people, or did you go for do a pattern from here? You only got to 8. Okay. I have done them personally up to 8. I have never tried to do it with 10, but this is where you can start to see the pattern, right? If you have this many numbers, you can start to see the pattern. And what's the next one you said?
35.
35. Can you tell me how to use the pattern to get that 35?
Your Pn equals Pn minus 1 plus 2n plus 1.
Nice formula. Great. So to get the 8, right?
Yep.
You're saying take the number right before it, the 3, add the 2n, the 4, and then add 1 more, right? So, and then plus 1 more, right? So 3 plus 4 is 7, plus 1 is 8. 8 plus 6 is 14, plus 1 is 15. 15 plus 8 is 23, plus 1 is 24. 24 plus 10 is 25, plus 1 is 35. So the formula, and you just gave me the formula for it, you said T sub n,
Tn minus 1.
right, which is just the number right before Tn, right? Plus 2n, the number from the column labeled 2n, yep, plus 1. You can come up with an explicit, but it's pretty hard for this one, so it's okay if you didn't get it. So 35 plus 12 is 47, so this will be 48.
And then your answer to the next question is actually the next sequence of pairs.
Oh, for 7 pairs, it would be 48 plus 13 is 63. Good. So right, so when you have a sequence and you have absolutely no idea what the rule is going to look like, it takes a lot of like exploration and studying and trial and error to try to find a pattern, right? Lots of juggling, yeah. So today, we're always going to look for the same kind of pattern, right? So we're just going to study one special kind of pattern. All right, so we're going to talk about sequences in the context of population growth and population growth models. All right, so a population growth model is a way to describe how a population is growing. And that population could be humans or rabbits or dollars in a bank account. So, so we're going to talk about populations as a sequence of numbers. So for example, we could write the populations of Greenfield on January 1st of each of the last 20 years, and that would just be a sequence of numbers, right? It would just be an ordered list of numbers, and I would use my notation for sequences to give the address of each number, right? So P sub 0 would be the size of the initial population. P sub 1 would be the size of the population after 1 unit of time has passed. P sub 2 will be the size of the population after 2 units of time has passed, etc. Okay, so we're interested in transition rules, the rules or the formulas that you can use to describe how the population is changing at each transition. So one specific kind of growth model is a linear growth model. And in a linear growth model, a population grows or shrinks by the same absolute amount at each transition. The sequence that results from linear growth is called an arithmetic sequence. We talked about this last class. When you always add the same amount to get from one number to the next, that's called, the result is called an arithmetic sequence. The resulting list of numbers. The rule is called a linear rule. Okay. A linear growth model needs 2 pieces of information to be able to describe it. You have to know how much you start with and how much it grows by at each transition. So here's an example. We have a nuclear reactor, has a 100-ton tank for storing high-level radioactive waste. There are 35 tons of waste in the tank already, and the reactor generates 5 tons per year. I want to create a recursive and an explicit formula for P sub n, which is going to represent how much waste is in the tank after n years. All right, so let's start with recursive. So recursive, that means that you can use previous numbers in the sequence, right?
Yeah.
Like, if I want to know how much waste is in this tank in any given year, if I know how much was in it last year, how do I figure out how much is in it this year?
Add the new 5 tons.
Add 5 new tons, yeah. So I just take however much was in there last year, which we denote P sub n minus 1, and add 5. There's my recursive rule. And if I'm going to use this rule, I do have to have some place to start. I would have to say P sub 0 is 35. Right? Otherwise, I have no number to start creating my list with. Yep, that says n minus 1. All right, and then if I want to write an explicit rule, when I write an explicit rule, the only thing I'm allowed to use in there is an n. I can't use any previous number from my list. Okay, so how could I figure out how many tons of waste are in there, knowing that I started with 35 and I add 35 every year?
So you're
Yeah, Garrett?
N times 5 plus 35.
Yes. So you're starting with 35, right? So you've got 35 in there, and then you have to add 5 every year for n years. And repeatedly adding 5 is the same as multiplying.
So 35 plus 5n.
You got it. 35 plus 5n. Start with 35, and then you add 5 every year for n years. Okay, so we have recursive and explicit formulas, and then we want to determine how long it will take for the tank to fill up. Right, so anyone have a strategy? How long till we reach the 100-ton capacity? All right, so why are you doing 100 minus 35? Right, because there's already 35, so that means we have 65 tons of room. Divide that by 5. And you get 13. Yeah, so 13 years. Anybody have a different approach? Yeah, we could start with our explicit formula. And the question is, how long, right? Which variable, n, it's the same thing, yeah. N is representing years, and P sub n is representing amount of waste, right? So if you make the P sub n a 100, and we solve for n, the number of years, you're going to end up doing the exact same steps you did over there when you solve this equation. First thing you're going to do is subtract 35, right? So we get 65 equals 5n, and then the next step would be divide by 5. So you get n equals 13. Yep. So this was, we just kind of logicked it through what the steps needed to be. We can use algebra to set up an equation, which is the exact same steps as what we did over here. Another thing you could do is you could make a table, right? You could do n, P sub n, and when n is 0, it's P sub n is 35, because we start with 35 tons in the tank, and then just fill this table out until we hit P sub n is 100. So we'd have 40, 45, 50, 55, 60, and figure out what n value gives me the 100.
13.
13.
Just saying.
Yeah. That make sense? Okay. All are valid approaches to solving that, to answering that question. The 5 in this formula, we have a 5 in the recursive and we have a 5 in the explicit, right? That 5 is called the common difference because 5 is the difference between the populations in any 2 successive years, right? So like P5 would be 35 and 25 is 60, and P6 would be 65, right? If you subtract those two, you get 5. So that's why we call it the common difference. Question?
Can you say that one more time?
Yeah. So it's the 5 is the number that you, it's a weird thing to name it because the way we've described it is it's the number that you add, right? But a difference is the answer to a subtraction problem. So we call it the common difference because if you take any 2 successive years, like the 5th year and the 6th year, and subtract them, you get 5. So it's called the common difference because if you take any 2 years and subtract them, you get 5.
But they have to be back to back. Like you couldn't do 5 and 8.
Right. They have to always be the same. Yeah. Yes. Oh, yes. The years have to be back to back. Yep. All right. In some cases, you're given different starting information. I maybe won't give you how much you have when you start and how much you grow by, but I can give you, say, P3 is 28, right? So in year 3, my population was 28 whatever's bacteria or something. And in year 6, the population was 40. And I'm telling you it's a linear growth model, right? So that means you know it grows by the same amount every year. So take a few minutes and see if you can come up with a formula, recursive and or explicit. You can try to do both using that information. I put up a little hint by putting up a table of values and filling in some of them, right? So translating the information they gave you that P3 is 28 and P6 is 40, if you make a little table with N and P sub N, it's easier to see how things are changing, right? So by how much did my population grow from 28 to 40? How much growth is that? 12. And over how many years did that take place? 3. So you grew by 12 bunnies over 3 years. So how many bunnies per year is that?
You get a lot more bunnies.
4. Yeah. So we did 40 minus the 28 and got 12. And then we took the 12 and divided by 3 years and we get 4 whatevers per year, right? 4 per year. So that means that if my growth is 4 per year, then 28 in year 3 should grow to 32 in year 4. Increase by 4 again, 36 in year 5. And when we increase by 4 again, we get 40 just like we should. Okay. All right, now how do you go backwards in the list? Subtract 4, so I should have 24, 20, and 16. So this is my starting amount. Yep, that's good to know. And my common difference is 4. So let's try to do a recursive formula. So P sub n equals what?
P and negative 1 plus 4.
And you also should give the starting amount.
Starting amount of 60.
So that we know, so we have some place to start applying the rule. Good. And then for explicit, P sub n equals what? 16 is our starting amount. Start with 16, and then you add 4 every year for n years. Very good. I don't hear quite as much conviction in your voice when you say that.
Just saying I still do.
Okay, so here are some formulas that you can use. You do not need to memorize them because we just solved two problems that involved these formulas without knowing the formulas. So you can always just think it through, but these are the formulas for linear growth. A recursive formula, you should always give the starting amount. And then P sub n is equal to P sub n minus 1 plus whatever the common difference is. And your explicit formula is always P sub n equals your starting amount plus n times the common difference. Okay, so we have a manufacturer that currently has 387 widgets on hand. Well, it used to be a made-up thing, but
You know what it is?
but it really is a thing now, right? It's
Really,
something
it's
in.
a little scrapey, like a one razor blade scraper. It's called.
Oh, okay. Oh. All right, so he has 387 widgets. During the next 2 years, this manufacturer wants to increase his inventory by 37 widgets per week. Okay, and you can assume there are exactly 52 weeks in a year. I want you to try to answer A and B, and then A, B, and C. Try to do this number 9 on your own, and then we're going to give this question a new wrinkle in a minute. Okay, so how many widgets will we have after 20 weeks?
1127.
1127. How'd you get that?
I did the recursive method again, equaling p minus n minus or p equals n minus 1 plus 37.
Okay, so there's you used the recursive formula. You came up with a formula first.
Correct.
Some people are much more comfortable writing the formula first and then using it to answer this question. Some people like to answer this question and then use that information to help them write a formula. Totally personal preference which one you do first. And you need your P0 of 387. Okay.
Because that's actually the plug-in for your PN.
Okay, so if I want P20, right, I want to know how many there are after 20 weeks. How do I get it?
So oh, actually, no, I'm sorry. I used the explicit.
The explicit formula, which is what?
PN equals 387 plus 37n. That's what I used.
Okay. And then if you want P20, you just replace this n with a 20.
Correct.
Right. So we want 387 plus 37 times 20. And you get, what was it?
720 for the 37 times 20. 387 plus 720. That's 11.
Okay. And some people would have done that without the formula, and it's totally okay if you just thought it through and said, oh, 37 widgets a week for 20 weeks. Okay, I'm going to multiply those two, and then add how many I had to begin with. Right.
I think I actually did just do that, but it was from the explicit.
Yeah. All right, so then we have our recursive and our explicit formulas. And then how many weeks until we have 720 widgets? 9 weeks. Okay, so I saw what you did on your paper there, and it looks like you said, all right, 720 minus the number I started with, right? So that means I made how many widgets? 333 widgets got made, right? And if you can make 37 per week, we would do that 333 widgets, divide that by 37 that can get done in a week, and that will give you 9 weeks. Right? So perfectly acceptable way to think through that answer. You could write an equation, right? N represents the number of weeks. So I'll be solving for N because that's what they asked me for. And I'm going to make P, the population, 720. So I would do 720 equals 387 plus 37N. And the steps to solving this equation are the steps we just did, right? The first thing you would do is subtract 387 from both sides. So you would have 333 over here equals 37n on the right.
We actually made it just a little simple.
Yeah, what did you do?
PN minus PO divided by 37.
Yeah, so you made it more general. PN divided minus PO divided by 37.
Yeah.
7 under the 333.
That's the number that you made. And then divided by, you can make 37 each week. So how many sets of 37 are there? And that tells you how many weeks you needed to make that.
There's 9 equals 10 if you want to.
Yeah, I switched it.
You swap it around because it's algebra and I can do that.
Because equal signs can be read backwards and forwards.
I know.
All right, so does this feel comfortable? Okay. So just to summarize, in a linear growth model, you always add the same amount at each transition. Okay? And the sequence that results is called an arithmetic sequence. All right, so we're going to add a small wrinkle to this widget problem. Let's say the widget manufacturer is trying to build up his inventory rather than put all the widgets on the market at once. He's going to store them up. And there are reasons that manufacturers do this. Like sometimes like a produce company will store up a bunch of apples and they have special chemicals and gases that will keep them from going bad. They'll store them and then release them into the market when the supply is low, right? Because then they can get a better price. So sometimes it makes sense for a manufacturer to store their stuff, wait till supply is low, and then release it into the market and get a better price.
And they also may want to store their stuff because they're getting it cheaper to their pieces and parts so that they can make them at a lesser rate than to make what they're going to get out of them when they sell them.
Mm-hmm. Yep. Okay, so let's say he's trying to build up his inventory. So he's going to save all these widgets that he makes. But the wrinkle is that it costs money to store stuff, right? So let's imagine it costs $10 per week to store a widget. And he plans to store all of his widgets for the next 2 years. How much will he spend on storage? So let's just think about the original 387 widgets. How do we figure out how much it will cost to store those? For just the 387 original widgets. So you multiplied by 10?
10.
How many weeks are in 2 years though?
104.
Okay, you're on the right track. You're on the right track. That's how much it costs to store them for 1 week. So if you take the original 387 widgets, right? Multiply by $10 per week, right? And over 104 weeks, right? So 387 widgets, each one costs $10 each week to store, and we're going to...
One? Oh, see, I didn't know that. That's not what it was saying. It costs him $10 a week to store widgets.
To store a widget. Yes, a single widget costs $10 per week to store. Yeah. So we take all 387. We have to be charged $10 every week for each one for 104 weeks.
He's not hanging on to them widgets. He's going to put them out in the market because it's $402,480.
$402,480.
Yeah, that's crazy.
Yes, storage is expensive. Oops, what did I do?
Yeah, but he's got to put the 37 a week out of the market.
All right, hold on. Let's just see how much it would cost him. Okay, so $402,480 just for those original 387. Now let's say he's one week later, he's going to have 37 new widgets, right? And he's going to put those in storage. So my 37 new widgets, they're going to cost $10 a week to store. How many weeks do we have to store them? 103 weeks. Because for that first week, they didn't exist. I made them that week. So I only have to store them for 103 weeks. Oops. Well, let's just see how wild it is. Let's just see how much this adds up to. 37 times 10 times 103 weeks, $38,110. Okay. All right, and then my next set of 37, they cost $10 a week, and how long do they have to be stored for? 102. So, because these are the widgets I'm making in week 2. So for week 1 and week 2, they didn't exist, which means I only have to pay to store them for 102 weeks, because the first 2 weeks of my 2 years, they didn't exist.
The first week was free except for the 387, and then you have to add all those things together by the time you get to the end of the 2 years.
Yeah. So let's see. 37 times 10 times 102, 37,740. And so each week, how much does my storage price go down? $370, yeah, because $10 per widget, 37 widgets. So in my next week, I'm going to do 37 times 10 times 101, because this is the 3rd week. These 37 widgets didn't exist for the first 3 weeks, so that means they only have to be stored for 101 weeks. And I can just do minus 370. Whoops. What is it? 37? All right, so then I have to do this. Like, this is, let's call this cost for, that's a fixed cost. This will be C1 for cost, C2, C3, right? I get to add up all these costs, plus this guy. Right? This guy we're going to set aside because we'll add that at the very end. But these guys I need to add up. All right, so I need more room, I think. So I have $38,110 plus 37,740 plus 37,703.
That wasn't right.
Oh yeah, that was wrong. 37,740 minus 370. 37,370 plus, and I don't want to write these all out, right? Because I have 104 of these, or 103, right? Because the first week, yeah. Yeah. So the very last set of widgets that I create, how many weeks will I have to store them for? 1. All right, so I'm going to have $370. Does this make sense? Now I have to add these all up. And it's got to add up to some number. I just don't know what it is. What do we do in math? What do you call a number that you don't know what it is? X or N. Yeah. Give it a letter. Say, those have to add up to something. There is some answer. I just don't know what it is. So my, yeah, I don't want to go through all of this. Yeah. So my trick is that when you add, you can add backwards or forwards and you get the same answer, right? Okay, so I'm going to add them backwards. I'm going to do 370 plus blah, 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 plus 38,110. Also, we'll add up to X. Okay. Then I'm going to add my 2 equations together. 38,110 plus 370. 38,480, yeah. And 37,740 plus 740 is also going to be 38,480. And 370 plus 38,110, right? 38,480. And what's X plus X? No. 2X. Yeah. X times X is X squared. Right. Okay, how many 38,480s am I adding together here?
103.
103, right? Because my first week was free because I was making my widgets. So I start with 103 and I have to count down to 1. So that means that I have 103 of these. And adding a number to itself 103 times is multiplication. So this is 38,480 times 103 equals 2x. And then I just have to divide by 2. And I'll get x equals 1 million plus your 400,000 from the original 387.
So he's not storing these widgets.
He's probably not going to store his widgets, yeah.
Keep the cash flowing.
So this is a very tricky thing, adding up the numbers in an arithmetic sequence. This is a little trick, and I have a way to shorten it. I wrote it in this box here. It's called the arithmetic sum formula. If you're trying to add a long list of numbers together, if the numbers in that list happen to form an arithmetic sequence where the difference between each successive number is always the same, in our case that successive difference was 370, right? To get the answer, you just add the first term and the last term, multiply the result by the number of terms, which was for us was 103, and then divide by 2. So I'm going to let you play around with one for a second. Remember the nuclear reactor problem. It currently has 35 tons of waste, producing 5 tons per year. The town in which this reactor is located decides they're going to charge a tax on the company that owns the reactor. And each year, the town is going to charge the reactor $1,000 for every ton of waste that it is holding in storage. Assuming the tank isn't emptied, how much will the reactor pay the town over the next 5 years, starting this year? So altogether, how much will the reactor pay the town over 5 years? Okay, let's discuss it together. This year, year 0, there are 35 tons of waste in the tank, right? So the town inspector comes in and looks at the tank and says, oh, you have 35 tons of waste. We're going to charge you $35,000. That's the rule. They charge $1,000 per ton. Okay, so $35,000 is the tax assessment for this year. Next year, which we'll call year 2, right? What is the tax assessment going to be?
It's going to be an extra $5,000.
Right, so $40,000, right? You did an interesting approach. It should also give you the same answer, but I'm going to do it a little different.
I know, but I screwed it up anyway.
So. Oh, okay. So $40,000 is what they're charged in year 2, because every year there's 5 more tons of waste. So the inspector comes a year later, says, oh, now you have 40 tons of waste. We're going to charge you $40,000. The next year, there's 45 tons of waste, so they're going to be charged $45,000. And then 50,000, and then 55,000. Now, when your list of numbers that you're trying to add up has only 5 numbers in it, it's easy enough to just type it into your calculator, right? So we could just add them up by typing it in. 35,000 plus 40,000 plus 45,000 plus 50,000 plus 55,000. Oops. There we go. All right, and you get 225,000.
I know where I screwed up.
$225,000. Okay, but there is also a rule you can use if the numbers in your list of numbers happens to be arithmetic, right? If the pattern happens to be that the numbers always go up by the same amount, in this case $5,000, you can use that little formula from the box that says Just add the first term and the last term, multiply the result by the number of terms, and then divide by 2. Okay, so I would add my first term and my last term, 35,000 plus 55,000, 90,000. Multiply by the number of terms. How many numbers are in that list? 5 numbers in the list, and then divide by 2. 225,000.
Yeah, that's where I should do that. I was trying to do it the simple way, and I missed by 25,000 because I forgot about the increases per year for each of the things, because I did the 5 terms at 5,000 each and added them instead of doing the term factor.
Michelle, where did we mess up when we were doing yours?
Gone up by 10,000.
Oh, you had them going up by 10,000 a year. Okay. So we end up with $225,000 in total gets paid in taxes. So it's not as hard as it seems in the last one, right? What made the last one hard is that the only thing that was hard about it is that the list was longer, right? So we had to figure out how many numbers were in the list and what the last number was. All right, so now I have a little bit more for you to work on, and this is a case for wind and solar.